So we had 50.0 milliliters of HCl, and it was 0.10 mole per liter. We had 50 milliliters sodium hydroxide, and it was 0.10 mole per liter. Initial temperature, 23.5. Final temperature, 30.1. Always write down your initial data first, so you know where you're working from. It says, what is the molar enthalpy of neutralization for HCl? You've got to pay attention for which substance they want the molar enthalpy for, because that's the number of moles you're going to need. If you don't know what the symbol is for molar enthalpy of neutralization, if you don't know what the X is, just put X. Okay? This is molar enthalpy of neutralization in terms of HCl. Uma, what are the units on molar enthalpy?
Kilojoules per mole.
Mm-hmm. Kilojoules per mole. So we need kilojoules, we need moles. We need moles of the system. What is the system going to be in this case? What are we talking about? Yep. HCl, neutralization of HCl. So this is your chemical reaction. I haven't put the states in. They're all AQ except for water, which is a liquid. So there's your chemical reaction. Your system is going to be HCl. So when we calculate the moles for the system, we're going to use HCl. What is the formula, the math formula that we use for the system? We have two formulas. One's for the surrounding, one's for the system. Not, there's two.
The molar enthalpy?
Yeah.
It's a change of H, which is enthalpy equals moles times molar enthalpy.
Well done. So this is how we're going to find the molar enthalpy, because this has to do with the system. So in order to do that, we're going to need moles of HCl, and we're going to need to find the enthalpy change for the reaction of these two substances together. How can we find the the energy change for the system? What mathematical formula do we need to use? Saeed's already alluded to it. You have to use other data, otherwise it wouldn't be in the question. Nikita?
Q equals MC.
Yeah. We get the information from our system, so Q equals MC delta T. Saeed said that delta H is equal to negative Q. The change in the surroundings is equal to the change in the system. So we can move forward. When you start with a calorimetry question, 9 times out of 10, you calculate Q first. From Q, you go to delta H, because most of the time we're asking for this. Occasionally, you get a tough question, and they're actually asking for one of the temperatures. Okay? So from here, Q equals MC delta T. What did we take the final temperature of? What did we take the final temperature of? Hydrochloric acid? Sodium hydroxide? Salt water? Spencer?
Sodium hydroxide.
Nope. Final temperature. Salt water, yeah. This is for when we take our final temperature, this is after we've mixed the substances together, right? We've mixed the substances together. When we've mixed them together, how much substance did we have in the beaker? A 100?
100 grams.
Well, you're jumping ahead. 100 milliliters. We have 100 milliliters, right? We had 50 mils of acid, 50 mils of base, added them together, and we got a reaction. So at the end, we have 100 milliliters of solution. So that is your mass in your calorimeter. It's the final mass of your solution after the reaction. So we have 100 milliliters. One of the assumptions that we make about calorimetry is that it has the same density, specific heat capacity as water. So this is one of those little things that you have to show. You can't stick milliliters when it says mass. You have to stick in mass. So you show the conversion. Show the conversion of milliliters to grams. And now 100 times 4.19 joule per gram degrees Celsius times 30.1 minus 23.5 degrees Celsius. So somebody with a we've got 0.005 moles of acid. So when we plug it back into this formula, now you can solve for the molar enthalpy. Awesome, thank you. Anybody else get that number? Kyle, cool. For the other question 8. Okay, don't look down at your page. Don't look at the question for the other number 8. Just find a blank piece of paper somewhere, and I want you to write down all the data that I tell you. So I'm going to read the question out for you. The molar enthalpy of solution. So the molar enthalpy of solution for ammonium chloride is plus 14.8 kilojoules per mole. So write that down. The molar enthalpy of solution for ammonium chloride is 14.8 kilojoules per mole. What is the final temperature when 20.0 grams of ammonium chloride 20.0 grams of ammonium chloride is added to 125 milliliters of water, so 125 ml water, at 20.0 degrees Celsius. What I want you to do right now is I want you to circle, 20.0. I want you to circle any information there that relates to the system. Put a circle around anything you think belongs to the system. Put a square around anything you think is the surroundings. So there's details in this question that people might miss first off the bat. So let's see how well you did. It says the molar enthalpy of solution. So we've got the molar enthalpy of solution. Don't write this down. Of ammonium chloride. And this is 14.8 kilojoules per mole. How many of you wrote that information out as a sentence? How many of you wrote it down as a symbol? How many of you just wrote the number down? Okay. It's telling you right there what's happening in this reaction. It is telling you that you are doing this. Molar enthalpy of solution. So you're dissolving a solid. You know it's a solid because the mass of it was 20 grams. You have 125 milliliters of H2O and the initial temperature was 20. Ooh. That's my bad square. Started out as a circle. So that's the only information that is for the surroundings. This is for the system, and this is for the system.
How do you know the difference between that? Like if you have like a bigger question, like.
So maybe it's something you've never seen before, and then I give you an example and you've got to kind of figure it out. Ask yourself this question. I always ask myself this question whenever I read a question for enthalpy. I always ask, what am I taking the temperature of? Whatever you're taking the temperature of, that's your surroundings, right? Because your surroundings is the only one that includes delta T. Anything else must be your system, okay? It's a good way to approach it.
Okay, so H2O is the surroundings then?
Yeah. unknown is contained in delta T. It wants to know what the final temperature was. So you have to go in the opposite direction. So you are going to need the molar mass of ammonium chloride. And where'd you have that? Nikita, you do?
3.50.
Say how much?
53.50
53.50 grams per mole. Okay. So we found delta H. Delta H is equal to negative Q, so Q is equal to negative 5.5327 kilojoules. Now, going to plug that in. Oh, oy vey. Q is equal to MC delta T. It's water. Got 125 milliliters. $125 grams times the molar, the specific heat capacity of water. And that's negative 5.5327. Now we have a problem. If I put this number in as it is, I've got kilojoules here, joules over here. You've got to have the same unit. How many kilojoules are there? How many joules are there in a kilojoule?
There's 1,000 joules.
It's 1,000, so I'm usually cheat. And I put times 10 to the 3 joules. Sorry. I cheat. And let's see if I can move this up. It's all come. Right? If I know my kilojoules, 1,000 times that number is my joules. So take that, and now you've got minus 5.5327 times 10 to the 3 joules divided by 125 grams divided by 4.19 joules gram degrees Celsius equals delta T. So you take your, oh my God, you take your energy, divide by the mass and the C, and you're left with delta T. What number do you get? Well done. That's the enthalpy change that goes in to your thermochemical equation. When this is your coefficients. You get your coefficient from your balanced chemical equation. Okay? So the units in your thermochemical equation are always going to be kilojoules. They're always going to be kilojoules, never kilojoules per mole. So I've given you an example below, and that's for the combustion of methane. If you look at these equations, one of them's a little easier to read, and that's the second one. Delta H is equal to negative 890.8 kilojoules. So, for every 1 mole of methane that's burned, and I say 1 mole because the coefficient in front of methane is 1, you produce 890.8 kilojoules of energy. So this is an exothermic reaction. Your delta H is negative. Another way to say that is to say energy is produced. That's why in the previous reaction, the energy is added in like a product.
NH3, and then let HR equals negative 92.3 kilojoules.
Yeah. Well done. Now, Nikita, what'd you do for the second one?
2H2O plus 483.6 kilojoules. Reaction equals 2H2O.
Yep. Ooh. So this one is endothermic. So it's plus 483.6 kilojoules. Okay, beautiful. So that is 2 ways to represent the data. There's 2 more ways. When you're asked to represent the data, you have to be given enough information, and it's usually given in one of them. So they'll give you one and ask you to give them the others. So the third way to represent thermochemical data is with molar enthalpies. So the energy change for 1 mole of reactant or product is represented. For example, molar enthalpy of vaporization. If the molar enthalpies are determined under SATP, they're called standard molar enthalpies and have a little circle as well. The molar enthalpy change for the formation of water vapor is negative 241.8 kilojoules per mole. Thermochemical equation that represents this is given to you below. Anything weird about that? Nikita? There's a half. So you know how I've told you when you balance, you can't have half a molecule? Thermochemical data you can. And it's only because this represents the formation of 1 mole of water vapor. You can change this. You can change this to 2H2 plus O2 goes to 2 H2Os, What do you think you're gonna have to do for your delta H? Times it by 2. So your delta HR for this one would be minus 483.6. Yep. Yeah, oh, I'm sorry, I thought you had a question. Okay, so, you could write it like this. We're gonna get to the molar enthalpies of formation. You can only have one mole of product for that, so you will get halves in your coefficients, but don't worry about it. So you can go from thermochemical equations to molar enthalpies and vice versa. Then you've got energy level diagrams. These are potential energy diagrams. They're on the back. We don't know where they start and where they end. So there's no quantitative values on the y-axis. There's no numbers there. We'll only ever know the change in enthalpy. So we can put that number in. But again, that's delta HR. So if you have an exothermic reaction, delta H is negative. There's less stored energy in your products. It went into the surroundings. Endothermic reaction, energy came from your surroundings, went into your system, so your products have a higher potential energy than your reactants. Think about it as stairs. Is it easier for you to go down a set of 20 stairs, or is it easier for you to go up a set of 20 stairs? Down's easier, right? So you put energy in to go upstairs. So endothermic, you're putting energy in. Reactants are lower than products. It looks like a set of stairs going up. Okay? All right, I want you to do question 9, 10, and 11 from the second sheet. And Kyle, I'll give you back your sheets. You're welcome. This will take a bit of practice, but I have no fear.
WPA.